Okay. All right. This is our first video lecture with me trying to actually communicate to you with sitting here in my living room. Hello, living room. Lily, my dog, is sitting down there. My cat is probably going to jump on my lap at some point. But I think we will try to see if this works. Okay, so today we're going to talk about testing and why we do testing. It's probably pretty obvious, but some things may not be obvious, so we'll go through a bunch of that stuff. So first we should talk about what the rest of the semester is going to look like, and we are working on that. We have a bunch of due dates and everything, and those were sort of throwing out the window and trying to figure out what needs to be delivered and when. And so we're working through that, and we're going to make that available to you all pretty soon. There's going to be a new gamification table coming out. Kitty is working on that. We will get it to you as soon as we possibly can. So we're going to definitely do PDRs next week. We will definitely start videos, presenting videos again next week. So people will be doing the same thing that I am doing and trying to give you guys some sort of a video on their news report, and we'll make Slack channels and stuff like that for them, or threads in Slack for them. So watch out for that stuff coming. Basically, just try to pay attention to the announcement as much as possible. I know there's probably a lot of information coming at you. So sorry to inundate you with more and more and more information. Okay, so let's talk about testing. So why do we test? Well, we really want to validate the system will work in general. Basically that it's going to work the way that we want it to work, and the way that or over a period that we want it to work. And we basically want to probe what problems that may occur outside of just sitting on a lab bench. Sitting on a lab bench is one way of testing things, but that's not really a good way of testing stuff. And so you want to try to test in an environment in which it will actually be used, and make sure that it works in that environment. Hope. I have heard a lot of people basically talking about like, hope it works. You should never use a phrase like that, like hope it works. No, there should be no hope. Engineers never want hope. They want to test and make sure that it works. If you need hope, then you haven't tested enough. And so testing, like what kind of test can you do? Well, you need to think about like what type of things could actually go wrong. What type of temperatures could my whatever it is that you're testing see? What type of accelerations could my contraption experience? What type of environment might it see? Will it see rain? Will it see salt? Will it see sleet? Will it be just nice and sunny all of the time? Whatever. And then think about like as you're building stuff, what could go wrong as you're building stuff. So like soldering, battery placement. So like if you put a battery on something and then you start shaking it around, could the battery just pop loose? That could cause issues. Coding, there's lots of coding issues. Could you actually like make a mistake and allocate memory or something like every time you go through a loop, and then it just grows and grows and grows and eventually just stops working because it has sucked up all the memory in the system. One of the things that I've seen happen on balloon payloads is students accidentally putting their Arduinos in backwards. And so when they get to the launch, they put the Arduino in backwards and they don't know why it actually isn't working. And they get very frustrated and just launch with something that actually doesn't work. And so how can you mitigate against that? How can you prevent these accidents from happening? Well, so with experience, obviously comes more ability to see possible bad outcomes. I think older people tend to be more pessimistic because they have seen what can go wrong. And so they know the things that can possibly go wrong. So brainstorming is actually really important. And as you gain more experience, you will understand more things that can go wrong. Testing plans become really important. So like what type of plans are you going to do for testing, for hardware, for software? And then usually these types of things are presented as a risk matrix, which looks like this. So a risk matrix has two different axes. Let's see if the mouse works. It does. So this is the probability. This vertical axis is the probability that something will go wrong. And this horizontal axis is the impact in case that thing goes wrong. And so if you have something that is low probability of happening and low impact, then it doesn't really matter. So you don't have to spend a bunch of time actually thinking about, like, I don't know, you write some data to an SD card without a comma or something like that. It is a low probability of failure and it has a low impact because you can mitigate against that. It's not a real big issue. But like putting your Arduino in backwards is relatively low probability, but it actually has a pretty high impact. So maybe you don't necessarily have to mitigate against that, but it has happened before. So maybe the probability is actually medium instead of low. And so you should think about like an impact, a way to mitigate against that probability and bring it down to a low probability. Like put an indication that says USB connector that way or something like that. So you think about how can you change the probability from medium or high down to low. And that's what really this risk mitigation or risk matrix is for. So you can see like, okay, this is really high probability and high impact. Well, how can we reduce it to low probability and lower the impact? That's basically the point. All right, so this curve here is a typical curve for the way things fail. And everything fails. Failure is not really an option. It's a fact of life. Everything fails. I will fail at some point. We will all fail at some point. The Earth will fail at some point. Our star will fail at some point. The universe will fail at some point. It's just a question of how long is it going to be until it fails. And so basically everything follows this type of cycle. So there are three types of failures: infant mortalities, random faults, and wear outs. And we'll go through all three of those. So infant mortalities, this is basically like when you drive a car off of the lot and then all of a sudden it just dies or something like that. And so something just goes wrong right away. And you reduce those by just testing and testing and testing and testing and making sure that like right out of the gate, things will work okay. This is like putting your Arduino in backwards. Like that is an infant mortality that you turn it on and nothing works. It's dead immediately. And so you want to figure out how you can mitigate against these infant mortalities. Like I said, testing, and testing. I have to say that the answer to all of these is testing. Okay. So what is this? This is the Chrysler Proving Grounds, which is way out on I-94. So Ann Arbor is way over here. It's far out. This is Chelsea up here. Oh no, up there, and you can drive off of I-94 and get off of I-94, drive down 52, and you come here. That's the proving grounds, and this is basically where they test the crap out of vehicles, Chrysler vehicles. And you can see that there is like this long track here where they basically just put miles and miles and miles and miles and miles on vehicles. This thing down here is like a brake test, so you can get going super fast along here, and then you can spin out. You slam the brakes on and see what's going to happen. Then this thing is like a slalom course, so you can drive through here and test high-speed turnings. This is like another turning type of test. Here, I have no idea what this circle is, but like I can imagine this is another form of turning test. You just drive literally in a circle. And then you have this long pathway throughout the whole thing, and you're not driving fast along there. You're just, putting miles on vehicles. Somewhere along here, they have a big hill where you drive like just up this hill, and they have like a hill that changes angles. So it goes from like a 7-degree grade to a 15% or 7% grade to a 15% grade to a 30% grade to like 100% grade. And you just basically keep driving the vehicle until you can't drive it up anymore. You're like flooring it, and you can't go forward anymore. And then you write down where you got, and then you back down. Yeah, I know about this place because my ex-wife worked there for the summer, because her dad worked here for like 30 years or something like that. And so she got a summer job. It was like the best summer job that she ever had, because the only thing she did was like drive cars around the tracks and drive over chatter bumps and everything. And it paid really well. So go get a job at the Chrysler Proving Grounds. I guess that's what this means. All right, testing cars. So the Ariane 5. Ariane 5 is an interesting case because this is a rocket. The first time that they launched this rocket, it exploded pretty disastrously. I would highly recommend that you watch any of these two videos here. I'll put a link in the show notes. I'll put a link down below the video, and you should definitely watch them. It's really interesting. It basically went up for a little while and then just turned over and then exploded. It was the first launch of this. And then what happened? Well, so what happened was that it was actually a software glitch. There was absolutely nothing wrong with the hardware at all. It was software. In fact, it was actually a piece of software from the old rocket, so the Ariane 4 rocket. But the Ariane 5 is actually a faster rocket, so the speed was larger than on an Ariane 4, and the software tried to convert speed from a 64-bit number to a 16-bit number. And I'm not sure if we ever talked about this, but bits and bytes, there's 1 0 1 0 0 1 0 zeros, etc. And what happens if the first bit turns from a 0 to 1, then many computers will turn that into a negative number. So you go from a number that's like 16,000, you increase it by 1, and it all of a sudden becomes negative 16,000. And your rocket goes from doing this to trying to do that. That's what happened. The overflow caused the guidance system to shut down. Because all of the redundant guidance systems were coded exactly the same way, they all shut down also. The attitude control system interpreted error messages from the guidance system as actual orientation data, which is very bad. So it turned over. The rocket started veering wildly off course, and luckily it self-destructed. So it could have actually gone down and hit a town or something like that. But as soon as it detected that it was going off course, it blew up. So the function that caused the cascade, the software glitch, was actually only useful on the ground. It was used to align the guidance system on the ground. It was not actually supposed to be used during launch, but they kept it on because it was easier, and they could have actually deleted that code. They just chose not to because it was easier. And so, you should make your systems less complicated, and you should take out software that's not important, and you should test the crap out of everything. All right, so random faults. Random faults are not really always random. You need to test against those random faults, and you can actually quantify like how often they actually happen. And if you buy quality parts, then you actually mitigate against random faults. So that brings up the idea of lot numbers. So one of the things that NASA does when they build satellites is they actually will buy a ton of extra parts for something because they're all made in a same lot. So for example, let's say that you're building something and you need a bunch of 400 kilo ohm resistors or whatever. Then you buy all of the resistors that were made on the same day by like the same person or the same factory or whatever, because they're all going to have exactly the same characteristics. So this plot is interesting because it doesn't actually even matter what it's showing, but it's basically saying, look, these filled things here and these unfilled things were built on a different day with a different lot. And we did a bunch of testing on those, and they performed differently. Building conditions change from day to day. So for example, the amount of moisture in a factory or the temperature in the factory can change. If you pull a car off of a line, it depends a lot on which day it's actually built or completed. It used to be, and it probably still is, like cars that were made on Friday afternoons are much worse than cars that were made on like Wednesday mornings. And it's just because like workers are in a different state of mind on a Wednesday than they are on a Friday. And so they do things differently, they behave differently. And so lot numbers are actually very important. And if you want these things to actually have very, very consistent testing and be the same from, thing to thing to thing to test to test to test, then you buy the same lot number, you buy the same resistors, you buy the same capacitors, and you just stockpile them and then you use them. And NASA actually has like these pages which will tell you like what an acceptable resistor is, where you can buy those acceptable resistors and all sorts of interesting stuff. And so lot numbers actually matter if it comes down to like how reliable or how quantifiably reliable something is, and how can you beat down those random deaths, basically. Random failures, I should say. All right, so then the final type of failure is wearing out. Everything wears out, as I said before, everything wears out. And the question is, where do you actually start this? What is an acceptable time frame for parts being worn out? And what can you actually do against this? So, so if you build things with super cheap parts, then you may actually start your distribution much earlier. So you buy some really cheap parts that wear out very quickly, and you'll have a lot of failures very early. But if you buy really super high quality parts that are really expensive, then maybe you push this off much further. And so, this can basically help explain maybe the differences between, say, cars, right? So you buy a car that really will only last a few years, and it's probably going to be super, super cheap. You buy a car that is super, super reliable, and it may cost a fair bit more because they're probably going to use higher priced parts. And they'll push this curve off further into the future. So that's really can really change the time to wear out, is the quality of parts that you actually use. Yeah, cars are a very, very classic example of this. Parts on cars wear out. They are designed to wear out. And basically, like, you know how long a part will last given its specifications. So this is interesting. Oh my gosh, this is totally out of focus. But this basically shows, this is really old. Sorry. This is something from like the USA Today from like 2005 or whatever. It's really funny. But it shows basically like different brands of vehicles and the problems per 100 vehicles, and the age of the vehicles. And so you can see that cars that are very young don't have very many problems, but as they gain in age, they have more and more and more problems. And you can see by brand that changes. So, Toyota is sort of the most reliable in terms of like least number of problems per 100 vehicles. And then you have Honda, Ford, GM, Chrysler, and then Volkswagen up here. Volkswagens have some problems where they did back in 2005, etc. You can actually see like on these links, I'm not going to actually click on them, but this link talks about the most reliable cars for like owning the first 3 years of a vehicle. How many problems do you have for different makes and models of cars, which is interesting. And then this link, this bottom link here, which I can't really see because the thing is going over it, talks about like what issues go wrong with cars. Like with this plot here, this isn't just for a vehicle, this is for every part in a vehicle. And so this lecture or this article actually goes through and it talks about like, when can you expect brakes to start dying? When can you expect belts to start dying? When can you expect your muffler to start dying, etc., etc. So that I found that really interesting. So hopefully you will too. This was super cool. So there's a backup site called Backblaze. It basically will back up your hard drive. You pay them like $5 a month. This video is not sponsored by Backblaze, but they sponsor a lot of podcasts. You can click on this. I'm actually going to click on this. So Backblaze has this thing where they talk about like what models of hard drives they're using because they use so many hard drives. For example, like HGST, they have 10,859 of these hard drives spinning. For this Seagate drive, they have 19,000. Here they have 37,000. And they talk about failure rates of each of these hard drives. So like the failure rate of HGST, this model is about 0.59%. And so, you can basically, in some ways interpret this as like Seagate's, this specific brand, you probably shouldn't buy for, if you're running a gigantic server farm where you're backing up everybody's hard drives, you probably shouldn't buy this one. But, this one or these might actually be really good for you. This one looks like it's really good, but they only have 99 of them. whatever. So, there's a lot of statistics in here, and you can go through like all of these statistics. Yes, and they're basically saying like which hard drives you should think about buying. Oh, I don't need to subscribe. Let me go back to this one. Okay, so if you want to see more discussion about this, like these hard drive failures, which are basically like they have infant mortalities, they have random failures, and they have wear and tear. All three are actually included in these statistics, but they don't differentiate. So, this video goes through and basically says like, oh, you should probably buy this hard drive versus that hard drive. It's an interesting video, but it doesn't do a very good job interpreting the statistics. This one basically says, don't worry about the statistics. And it's really interesting because it talks about like how Backblaze is just like buying just random hard drives and using them, but not all hard drives are made the same. Like what we were talking about here, like some hard drives are made to last not super long, and they're made to sit inside your normal desktop computer and not server racks and not high temperatures and not running 24 hours a day, 7 days a week, writing constantly. While some are built like that. And so you have to have an expectation that some hard drives are going to fail and some hard drives are going to last longer. So this one, I actually really like this video, even though it has significantly fewer likes than this other video. I think it's because it's poo-pooing things, but like it's clear that the guy actually put more time and thought into this. Yes. All right. Yeah. So I think, as I said, this, like the further you push this blue curve here, the wear out to the right, usually the more expensive things are. Like I said, you could probably buy a car, like you could probably make a car that only costs like $5,000. It would probably die right down here. Which would not be good. And so, instead of having a $5,000 car that dies here, you have, $12,000 cars that die, 4 years after you buy them. And then you have some cars like, a Toyota Prius is going to cost you like $25,000. As opposed to a Hyundai Accent or something. A Hyundai Accent will cost you $12,000-$14,000, and you'll get what you pay for in some ways. And so, like, you compromise. You pay for sort of what you get, which is interesting. This sort of shows that, this auto brake pad testing, which is super cool. This video, I really like this video. It basically takes a bunch of different brake pads and like puts them through just a ton of tests. Really super cool tests. You get to see like brake pads actually catching on fire because they're basically just like accelerating the car up to like 75 miles an hour and then putting the brakes on, and then you slow down to 0, and then you accelerate up to 75 miles an hour, and then you put the brakes on and you slow down to 0, just over and over and over and over again. And like the rotors like turn red because they're so hot. It's so cool. But yeah, I highly recommend this video. It's super cool. And basically what their conclusion is sort of like what I just said, that expensive pads are probably better. Not always, though. The mid-range pad actually turned out to be a pretty okay pad. But the question is, like, if you have a car that's like has 200,000 miles on it, for example, do you want to spend $75 on brake pads that are going to last, twice as long as pads that cost like $20? I don't know. It depends on like how often do you want to get your brake pads fixed? How important is safety? to you. So you basically weigh all of this stuff when you make decisions about like what brake pads to get. It's really interesting. In some ways you pay for what you get, but you can compromise and actually get lower, spend a lot less money, but you get a little bit cheaper of a product. Really interesting video. Definitely should watch it. 3 Sigma events. So most of the time what we do, I can't really say we because I'm not really an engineer. I'm more of a scientist. So when people test, they usually test for like one condition when one thing goes wrong. So for example, like how well does a tire handle potholes? And you basically can go over potholes and stuff like that. And so, how well will it do for potholes that are like normal potholes that are sort of like in the middle of a distribution function? So like a pothole that's, whatever, a few inches in size or something like that. And then you basically say, well, let's see how well it will handle 3 Sigma potholes. So like potholes that are like 3 feet across or something insane. Will your tire actually work under those conditions? How important is it to work under those conditions? Do you want to design a tire that can actually handle all conditions? And by all conditions, that's way out here in 4 Sigma land or something like that. So you can see like by 1 Sigma, you're dealing with 68.2% of all type of events. So like all potholes that are less than 1 foot or something might be 68% of the potholes. And then you might have 2 feet potholes that are out here. And then you might have like the 3 footers that are way out here above like 96%. And so do you want to be able to handle all of those types of events? So it depends on, how you want to design your system. I actually see, like, it's really interesting, specifically potholes and tires. You see, I watch a lot of YouTube videos on Tesla cars. And one of the things that like people on long road trips complain about, I've actually seen a few videos, is that they accidentally went over some big pothole and they got a flat tire. And the only way to change the tire with a Tesla is like to call Tesla and have like them send a mechanic out to change the tire. They basically tow it back to a mechanic shop, and then they change the tire at the mechanic shop. And so I think that one of them said that it cost them like $4,000 to change their tire, and like 8 hours. It's really insane. Teslas are so super cool, but they are so unbelievably expensive to like maintain, and if there are accidents. And this is like, they did not design a Tesla to handle the Michigan potholes. Okay, and then like if you do design like for Michigan potholes, well, did you design for things like making a hard left turn, going over a Michigan pothole, and it is pouring rain outside? And so you can actually like multiply these events. So how well does a tire handle super pouring rain? How well does a tire handle going fast around a left turn? And how well does it handle going over a pothole? And then how does it handle like in every combination of those things? And those are called like 3 Sigma, 3 Sigma, 3 Sigma events because you're like multiplying them together. So they're super, super, super rare events. But sometimes you actually do plan for those. And most manufacturers actually do plan for that type of thing because, when you have, the problem is that like, okay, let's look back at this distribution function. When you talk about like 3 Sigma events, that happens 4% of the time. 4% of the time are these 3 Sigma events. That's seems pretty rare for like a normal person, but you take 100 million people all driving vehicles, and that's a lot of events. You take the 4%, you multiply it by 4%, multiply by about 4%, and you still have thousands and thousands and thousands of those events every year by people who are driving cars and stuff. And so those happen. And so you do need to plan for those types of things. It's the same with like if you're on a satellite or you're designing a satellite. You may not think that these 3 sigma, 3 sigma, 3 sigma events happen very often, but if your satellite is up there for 2 years, it may happen for like 20 minutes or a few hours or something like that. And do you want your satellite to die during those few hours? So for example, like you have the satellite solar conditions, you're in like peak solstice, it's June or something like that, and you have bad local time of the ascending node, which is like the worst conditions for lighting, and then you're trying to put your satellite into a certain orientation, and then you need to transmit data during this particular horrible orbit. Like, could you drain your battery to the point where it will no longer work? You could lose your satellite. And so you have to plan for these types of conditions. All right. The other thing that I wanted to talk about is that over-engineering can actually cause problems. I really like this illustration. You take a log, you put it, or you prop it up on two positions, and so then it breaks in the middle. So you put some rocks underneath it, and then this side fails here, and then it breaks in the middle again. And so you've over-engineered, and actually you cause problems that way too. So there are a bunch of different podcasts and videos, or podcasts and an article that actually talks about this. So it's really interesting. So this podcast is called Cautionary Tales. It's episode 3. It's interesting. It starts off as sort of like not super engineering oriented. It talks about the issue that they had with the Academy Awards, where they said La La Land won the Academy Award when it was actually Moonlight that won the Academy Award. And they talk about like what caused that failure. And it was really interesting because like they wanted to mitigate failures. And so they made the system more complex. They put like redundant envelopes in. And then because they had redundant envelopes, they had like the envelope for the best actress, which was actually taken on stage and read, but because they had a second one, they accidentally handed that second one to the next presenters, who just presented, basically they misread it as the best picture. Interesting. But then it talks about like the relevance to actual engineering too. This paper discusses how complexity adds additional failure points. That's what I took this figure from that. It's an interesting paper. And then 99% Invisible is like one of my favorite podcasts. And they did like a little sub episode. They have these like mini stories episodes. And so this episode describes basically the 3 Mile nuclear power plant, 3 Mile Island nuclear power plant, which was really interesting, and the failures that actually happened there. And it's talking about like alarm fatigue and the fact that we basically all hear alarms like all of the time, and so when something fails, we hear an alarm and we just ignore them now because we're so used to alarms going off all of the time, and we've become desensitized to alarms. And alarms don't really tell us anything. They're usually just like a beep 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 noise, and they don't convey any information besides like something is happening. And so it's really an interesting episode. I highly recommend that too. All right, so the idea with all of this stuff is that you should sit down with your group, and you should think about like how your payload can fail. like what are the failure modes of your payload, and what do you need to consider when you're testing your payload. So like what issues will actually cause like infant mortality, random failures, and wear out of components. My guess is that you won't have any components wear out, but like these top two are probably really important. And so the idea is that you sit down with your group and think about like how could you mitigate against those, each of those things. I'm using a fidget spinner, and I wasn't supposed to pick this up because it makes a lot of noise. All right, so the main takeaway points for this video is that there are really three types of failures. There's infant mortalities, there's random failures, and there's wearing out of components. And so you need to test against all of them. There are different ways of testing against all of them, but testing is the best way to mitigate against all of them. Making systems more complicated doesn't always help. Like thinking about how can we mitigate against infant mortality? Well, let's make the system more complicated. That doesn't help, because when you make systems more complicated, there are more failure points, more ways that they could actually die. And so you need to think about like how can we make things simpler, and how can we mitigate against those failures. And that was all that I was wanting to talk about. I don't think that was too horrible. Hopefully you don't think it was too horrible also. And so I will try to do this for a few more lectures. And until I see you again, have a good day. I don't know. All right, bye-bye.